Hey, I'm going to go over a problem on how to deal with the electrostatic balloon lab. So what we've got going on here is we have a couple of balloons, and look, that's my pretty balloon that is tied off and has a string that comes up. And of course, there's another string on this side, and we have the same sort of deal going on. And just like in real life, perhaps they're maybe not the same height and same size, but they should be as much as you can, and you're trying to measure the distance between their centers, and you should of course also measure the distance to the center and that pivot point up there. We're going to call this L for simplicity, and we are going to call this R again for simplicity. So it's the distance between their centers. Okay, so what we want to find is we want to find the amount of charge that is on each balloon, and if I'm able to kind of move these off this, well, actually I don't even need that. I think I need to move them off to the side, but here we go. Let's look at the one on the right and look at the forces that are acting on this one. So if I were to just kind of draw in blue the forces that are acting on it, we have mg acting straight down. We have, of course, the electrostatic force acting off to the right due to the balloon on the left. And then, of course, along the string, we have this force of tension that is acting along the string. If I were to focus on that for a moment, in fact, maybe I can enlarge it a little bit just to make it easier, we can break this down into x and y components. So it has a component that is off to the left and a component that is up. Let's see if we can bring that back down. Okay, so let's realize something, that the vertical, and I actually did a decent job of it, the vertical component of the force of tension should be equal and opposite to the force of gravity. So to kind of start from scratch, I can say that the sum of all forces in the y direction is equal to, let's say, a negative mg plus a positive force of tension in the y direction. Right? So that's this part of the force of tension which is acting up, and then, of course, the negative direction of gravity. And this is in equilibrium, so it's 0. And that allows me to say that mg is equal to the force of tension in the y direction. If we were to measure this angle here, then that means, and I'll do it in green here, I guess, that this portion right here is going to be theta over 2. Right? So if this is theta, then the green one would be theta over 2. So I'm going to be referring to that as theta over 2 from now on. All right, so I'm going to go ahead and do a little substitution in here. I'm going to say that mg is in fact equal to the cosine of theta over 2 times the force of tension, because again, this is the adjacent side to the angle. Let me solve for the force of tension real quick. So just divide each side by cosine theta over 2. So the force of tension is equal to mg over cosine theta over 2. And I'm just going to kind of hang on to that, even start it for now. And maybe I can actually take all of this and move it to the left a little bit more. Give me some room. Okay, good. All right, let me change colors. I'll switch to green for you, and I'm going to worry about the x direction. So sum of all forces in the x direction is equal to, let's say the right is the positive direction, so I have the electrostatic force minus the force of tension in the x direction, because that's clearly acting off into the left direction, and that's equal and opposite. Sum of 0, so again, I just kind of say that the electrostatic force is equal to the force of tension in the x direction. Let's see, we know that the electrostatic force, and in fact maybe I can move some things up, make me feel like I have a little bit of room to work. So K times Q1 times Q2 over R squared would be the electrostatic force. And since the two balloons, we're effectively going to assume that they have the same amount of charge, because you rubbed them on your head or rubbed a bunny hide on them, and perhaps it would actually help if I just said q squared, right? q1 times q2, if they're the same q, would be q squared. And that's over r squared, the distance between them squared. And the force of tension in the x direction, that's the opposite side. Okay, so this is the opposite side to the angle. And so that would be sine, right? That would be the sine of theta over 2 times the force of tension. But wait, I already found the force of tension, so I'm going to substitute that in. I'm just going to work on the right side of the equation here. So the sine of theta over 2, remember that goes in the parentheses there, then times mg. Wait, that's over cosine theta, so that can go in the denominator here, over cosine theta over 2 in parentheses. All right, so look right here, sine over cosine, that is tangent. Okay, so we're looking at tangent theta over 2 times mg. Let me, since I'm running out of space, I'm going to start in the middle top here. So that means that k times q squared over r squared equals the tangent of theta over 2 times mg. All right. And now all I want to do is solve for q. So I can multiply each side by r squared, divide by k, and take the square root. Yeah, so k times q squared equals tangent theta over 2 times mg r squared. Divide each side by k. Oh no, I got rid of too much. I didn't like that. Let me just do it like this. Whoa. It's not liking something I'm doing. I don't want... Yep, it's really not liking me. It's the computer. It's not me. I'm going to scratch it out. Okay, it hates me. And so we're left with q. And if I just take the square root of each side, and apparently I can't erase, so I'm just going to scratch that out as well. And so I've solved for q in terms of having one equation I can work with. Sorry, I got to put parentheses around that. Those are parentheses, I promise. So that is my final equation. So given that I've measured theta here, the angle between the two strings, and I've measured the distance between the two balloons, then I can solve for q. By the way, rather than using a protractor to solve for that angle, the most reasonable thing to do would be to measure the length L in red, like I was talking here before, and measure R, and then make a couple of right triangles, and since you have L and you have R, you can find this angle here. It would be R over 2, right? It would be R over 2. That'd be this, right? That'd be R over 2. You have L, you have the opposite side, you have the hypotenuse, and so you can use the inverse sine of R over 2 divided by L. That should be able to get you half of the angle, which would actually give you theta over 2. Or you can just take a protractor and measure the angle between the two. But frankly, I think that measuring those distances is much more precise. At any rate, that should about do it. I hope that's helpful, and we'll see if we can do the lab in class, or if we've already done it, hopefully it's helps you with understanding where the numbers are coming from. And that's it. All right. Have a good one. Have a good one.